So, good morning, or good afternoon, or good evening, depending on where you are, and welcome to the 24th workshop on elliptic curve cryptography. This is an annual workshop dedicated to the study of elliptic curve cryptography and related areas. Here, we're talking about a related area with applications to elliptic curve cryptography, which is formal verification. So next year we'll hope to have a nice quarter century ECC workshop in Taiwan. But for the moment we're having the 24th edition in a more unstructured way in your office or in your living room or wherever you are. So welcome. We'll be following questions on the Zulip channel. So please go ahead and involve there. And then we'll also be around for the coffee break afterwards. So there are four of us here today. I have Bas Peters from Aus in Denmark. We have Baoya Wang from Academia Sinica in Taiwan, and Kartik Bhagavan from INRIA in Paris. So we're, well, not quite all around the world, but all over the place. And I'm Ben Smith. I'm also here in Paris. So what we're here to talk about today is formal verification of cryptographic protocols, of cryptographic code. And what I'd like to do is start by going around the table, so to speak, so that each of the presenters can introduce themselves. So maybe we can start with one of next year's hosts, with Bao Yao, if you want to introduce yourself.
Okay.
All right, you're unmuted now.
Okay. So good morning. So I'm Bo Yao, and I'm based at Taipei, Academia Sinica. So I do formal verification on crypto programs, and basically we're working at verifying very low level, like field or group operations in ECC. So for example, in OpenSSL, there are a bunch of assembly code for different architectures underneath all these 25119 or these P curves. And that's our target. So basically, assembly code or even very low level C code implementation for the ECC field arithmetic and even up to these group operations. We're trying to verify the programs are correct for arbitrary input in the specified domain. So that's it.
Great, thank you. Bas, do you like to introduce yourself?
Yes. My name is Bas Peters. I work at Aarhus University. We have a big research center here on blockchain, all aspects of blockchain. So there's a close collaboration between cryptographers, implementers of cryptographic engineering, and people from formal verification. So it's the COBRA or Concordium Blockchain Research Center. So with respect to elliptic curves, we have very close collaboration with Diego Aranya. He's an expert on the cryptographic implementations, and I'm the expert on formal verification. So I'm very happy to be invited here and to speak to this audience, because it's not really my core expertise, but I'll try to keep up. We're using tools like COC, Fiat Crypto, which is a library in COC. We're using EasyCrypt. We're using also using Jasmine, which is an assembly language, or a sort of higher level assembly language. And we've been working on so we're using the a very small formal verification with a very small kernel to actually check all the rules to the axioms of mathematics. We've also been working on other things. I put a link in the Zulip chat on some of the work we've been doing on implementing constant time field inversion, and this gives people maybe some sense of how much work it is. So we completely verified a paper on the Bernstein-Young field inversion, and this took about a year's of work. So this also gives an idea of how much time actually goes into formal verification. Thank you.
Thanks, Bas. Kartik?
Hi, I'm Kartik Bhargav. We have a team called Prosecco at INRIA, and we work closely with Microsoft Research and this thing called Project Everest. So the basic kind of set of things that we work on is how to integrate formal verification tools into the development lifecycle. So we work on verifying protocols like TLS, signal, noise, this kind of stuff, but also on a verified crypto library called Hacklestar, that you might have heard of. And the goal for this whole branch of things is to provide a set of tools that work for Rust, for high-level languages like F***, which generate code and things like C and WebAssembly and assembly. And you can really verify in one framework everything from your high-level protocol, including its security, all the way down to crypto like ECC and various other things as well, including AED, ciphers, and everything. So yeah, so that's the whole range of things we've been working on here.
Great, thanks. So I'm certainly not an expert in formal verification. Being in France, it's something that I've obviously been exposed to over time. France is notionally, there's no state religion here, but in practice there's formal verification. But it's something that I've always been really impressed. I've always been very, very impressed by. But also, the more I'm exposed to it and the more I see of it, the more naive I feel my questions are about it. So I've got a lot of naive questions. Bas was saying that he feels like he's coming to this from a bit sort of outside the community, but ECC has always been like a 1/3 elliptic, 1/3 curve, and 1/3 cryptography. So there's certainly, it's always been larger than just pure elliptic curve cryptography as a conference. On the other hand, it's not like elliptic curve and cryptography are three separate domains. Otherwise, we wouldn't have a conference. So there's so right here we're sort of forming the intersection here. One thing, like just the first thing, when I think of verification, I mean, I know there's verifying protocols, I know there's verifying code, I know there's even verifying hardware, and I sort of imagine a protocol stack or something like that, where you're proving protocols, you're proving the mathematics, then you're verifying the software, or even generating verified software, and then you're maybe even proving the design of the platform underneath. So you have all these layers. Is that an accurate sort of picture? Is it actually a stack of things like this with layers talking to each other, or is it just is it more horizontal or a complete mess in your view of things?
All right, let me go first, I guess.
Yeah.
Well, in an ideal world, it is in fact not just is it layered, but it's also modular. Right? In an ideal world, we're able to verify things, in modularly and compose the proofs together in a way that sort of gives you increasing amounts of confidence. I mean, one of the terms that a lot of people in the community have started using the last couple of years is high assurance cryptography, rather than saying verified cryptography, because verified sort of makes it feel like everything has been verified. Whereas what you're trying to do is really sort of increase assurance by saying, okay, I'm going to take care of this class of attacks, let's say, remote timing side channels, or, arithmetic correctness, or whatever, or memory safety. And you can either do that across the stack, or you can do that for one layer at a time. But in practice, I would say that there are different tools that are good for different layers. So there are tools like Cryptograph and EasyCrypt that are great for verifying protocols, constructions, and there are other tools like, Fiat Crypto and CryptoLine that Voya has been working on, which are great for verifying low-level crypto. So I have a feeling that pragmatically we would like to have a stack of tools attacking a stack of components. And if we can get them all to play nicely with each other in a formal sense, that would be amazing. But it's, to me at least, I feel pragmatically, even if you just get them working together, even if they're not all tightened up, it's kind of okay.
Boyo, you're, I gather, sort of working more on like the level of low-level implementations and verifying them. Do you have the same sort of vision?
Yes. So basically, I don't think any group in the world can do everything all levels at the moment. So we're trying to target one level and then work on that. And agree with Karthik. Ideally we're hoping in, I don't know, maybe in a few years, we're going to integrate all the layers to work together and to have a more complete picture for verify or high assurance crypto code. But again, Karthik is also right. So currently, that kind of integration is not really there yet. Okay, so most groups are doing our own work, and we talk to each other, of course, but there's really no unified framework to integrate every tool so at every level.
Okay.
Yeah, so I agree with Karthik. So the modularity is very important, and there are various aspects that we want to look at. So functional correctness, memory safety. One issue that we of course also still have is proofs in cryptography, not even computer-aided proofs, but just to have a good set of rules for how to prove a cryptographic protocol to be safe and have a modular framework for this. And there's quite a bit of activity around that area, but there's clearly a lot of work to be done, and there's some that's also clearly some place where the cryptographic community, I think, wants or needs some help from logicians and people actually comfortable in implementing proof assistance. For instance, about composable proofs, there you can see quite a lot of developments around this universal composability framework that's fairly informal at the moment, but there are a number of groups trying to make that more precise. So there's a lot of work around that area. One of the tools we're using is Fiat Crypto. That's a tool that takes you write your cryptographic primitives in the COC functional programming language, and then it reflects this into a small imperative language, and then it generates either C or Rust code, and then from there on you can go further all the way to hardware. And as an important part of this is a formal specification of hardware, and also about timings of operations on hardware, for example the RISC-V. And what we can hope to see in the coming years is that there's actually a fully verified stack where you go from something you write in mathematics, in COC perhaps, or in F-star, and then you actually generate something where you also have the guarantees for hardware. So there's certainly a lot of work going on there.
Okay. So Karthik, we'll come back to tools and modularity in the very near future. I just want to pick up on one thing there that Karthik, you were saying that that there's a difference between the goal of like a fully verified everything or high assurance for cryptography, where maybe almost everything is verified, but not quite everything. And Boyo, you were saying, well, no one code can do everything. Is there what can verification not do? What is sort of out of scope, or things that the three of you see looking at verification in crypto, and you think, okay, well, we can do all of it except that, or this is this is not provable, or this is
well, let me go first. And I guess it's as usual, in most, like we do in pen and paper proofs, one always has to set up your definitions and your model first, right? And in formal verification tools and frameworks, the setting up the model and the definitions is maybe 80% of the work. So sometimes we may not have the right model already in place for certain things that you want to prove. So let's take an example. You want to prove that your code has some countermeasure against speculative execution attacks, and you want to prove that your countermeasure works, or against fault attacks or whatever. Now, in order to even prove that your countermeasure works, you have to have a model of these kinds of attacks, and like Bas was saying, maybe even a model of the hardware. And even developing that model in a way that's precise and accurate might take you a long time. So it's not that it's not possible to do. It's just that it requires a different level of expertise and perhaps a lot of time to set up the framework before you can start doing these proofs. And that's also related to Boya's point, I think, about why certain groups focus on certain aspects. Because suppose you're going to be modeling RISC-V, it's going to take 2 of your 3 of your students like a couple of years. So might as well, like that group is just going to be doing the hardware level stuff. And another group might be doing like crypto proofs and mechanizing them in Coq or in EasyCrypt or something. And it's a completely different level of expertise that you're asking, right? So, and a different kind of time scale and different kinds of applications. So I think that's what I meant by saying that you need to split it up, because it's mainly about, I think, human expertise and what certain tools have been trained to do better than other things. And I would say less about this you cannot do. I think anything you can prove by hand, technically you can prove with a computer. So I don't see a fundamental limitation. I don't know what the others think.
So I agree. Anything you can prove by hand, you can also prove on a computer. There's some interesting aspects of combinations of proving and computing, and they're very clear examples, like the 4-color theorem, where there's you prove something on paper and then you do a big computation and you say, well, these things actually fit together. And then of course there's a lot of work to be done to actually make sure that if you want to write the full proof, how do you actually do this? And this can now be done in a proof assistant. So this is something that Georges Contier has done a couple of years ago, about a decade ago now, I think. So you can use your proof assistant to actually do very heavy computation, and proof assistants are getting faster and faster. And for instance, the Coq proof assistant will now be about as slow, about as fast as optimized or Camel. So and the whole compiler is actually verified. So things are becoming both very fast but also completely verified. So you can actually prove a lot more in the computer than you can prove by hand. Having said that, a lot of proofs are actually a lot of proofs on paper are not completely rigorous, and when you actually formalize them, that's certainly something that you'll soon find out. And there are also quite a few papers in cryptography about the crisis of rigor in cryptography. But also in mathematics, we find quite a few places where people are either a bit sloppy, and this is because, well, for professional mathematicians, this is typically because they have a lot of experience in that particular field, and they know that, well, this kind of proof attack will work, and if it doesn't work precisely in this way, they'll find another solution to this. There's a lot of intuition if you've been doing these things for decades. But also capturing that intuition and building that into tactics or decision procedures. There's a lot of work going on there, and there we can also see that we're getting a lot better than we were, say, a decade ago. So the proof assistants are improving a lot, and also the combination of automated tools like SMT solvers and proof assistants is also getting a lot better. So I think we're making a lot of progress.
Yeah, I guess I'd just like to come back a little bit and just say that, I mean, it's not so, I mean, things are getting better, but I would say that there is still a lot of work needed, of course, because I think regular members of visitors to ECC would be writing proofs by hand all the time, right? And a lot of those proofs use heavy amounts of intuition, as Bas said. And I don't think we have a magic formula for converting that intuition into something that machines can understand and check. It takes a fair amount of work before we can get the tool for a particular class of proofs to a point where, in fact, what you think, how you write the proof by hand can directly be translated into a machine. And in some cases, we never get there. It's not immediate for sure. but maybe it won't be too painful. It may take you a little bit more time, but not too much. And that's, I think, where we are, and we perhaps could do better. I mean, one angle, which is also a way of looking at things, is to specialize, right? So the way things have been working out is that people who come to use formal verification, they have a very, very specific goal in mind. I want to verify ECC, or I want to verify, this crypto construction. So they have very specific goals, but the tools that we build are very generic, because of course we want to build one verification tool that's sound, that's complete, that does all the proofs that you want to do. But that basically means that that tool may not have very specific sort of tools for your particular use case. So I think there is value in developing something, I mean, within a generic framework like COG, developing things which are more domain specific. And for example, fiat crypto is very domain specific, which is why it's so effective. And things like that, which sort of help do one particular kind of proofs very well. And that's what the kinds of tactics that Bas was speaking of as well, I think, are like that. And I think we are all figuring this out right now. So it's having a good set of target problems that we should be attacking. And that's would be very useful from the community to say, okay, this is what you're worried about. Focus on that. And then we can at least make sure our tools work well on those kinds of problems.
Right, thanks. Boyo, do you have anything you want to add to that?
Yeah, small addition. There's an interesting distinction between computer scientists and mathematicians. So mathematicians tend to see mathematics as one big cathedral, and it's it's one big building, and everything fits nicely together and builds on top of each other. So you have the certain subfields of mathematics, but they all fit nicely together. And this is because in your head and in your training, you just make the connections between the different fields. So obviously, elliptic curve cryptography works very nicely with abstract group theory. But for computer scientists, they think much more in terms of big software libraries and packages that fit together, and maybe a package manager and so on. And trying to get these two views of mathematics, or more specifically of elliptic curves, to fit together, that's still quite a bit of work needed there. For instance, also, if you want to prove something about elliptic curves, you may want to use some real numbers, but then it's a question about whether your generic real number library would work, or your generic library for group theory would actually work off the shelf. So there's an interesting distinction in vision between mathematicians and computer scientists, and I think there's also a lot of exciting work going on there, but it's something to be aware of.
Yes, I want to add that. So basically, to build tools to help mathematicians to do mathematics, I think that's one of the, topmost goals for building these proof systems, etc. But the reality is, even at the moment, the tools are not there yet. Okay, it's still impossible for average mathematicians to use, say, COG or Isabelle or whatever theorem proof we have to do their real work. And that's for a reason, because the mathematics is a very large field. So any generic tools for all mathematics just not, it's not going to be useful. So we need to specialize, and I think ECC is a quite good combination of mathematics and computer science. So for computer scientists, we can actually, try to learn the necessary mathematics and to improve the tools. Okay, so compared to other fields of mathematics, topology, so we don't have such intuition to do that formally, and that we just try to do this step by step, and eventually, again, I think for theorem provers, the goal is to build a tool to help mathematicians to do their mathematics proof, and I think we're beginning to see the improvement in ECC. Okay, so now, especially, I think Gansier, he has a library for group theory, right? And also for color theorem. So these are very useful tools for doing mathematics. And, we're trying to build more tools and libraries to do ECC mathematics proofs.
Yeah, it's an excellent point. So we've been talking about, the cathedral of mathematics, but also this notion of specialization. And so if we specialize from the Cathedral of Mathematics to the barrage of elliptic curve cryptography, Fabio Campos has this question, which is, does the domain of ECC, or can the domain of ECC play a special role in formal verification? Or are there techniques or tools within formal verification that are really well suited to this domain?
So I think the answer is yes, because of the unique position of elliptic curves. So it's an exciting community between, which include mathematics, people with a good mathematical background, but also people with that know how to implement things very efficiently. So people already have this dual side, and then actually trying to learn to write proofs in a proof assistant doesn't take too long. I mean, we also train mathematicians to use LaTeX, and we see how hard that can be. Coq may actually not be too bad. Certainly the notation is more intuitive than what you write in LaTeX. It takes about, say, if you take just a master student in mathematics and you train him for, say, a month or two, he can be useful in programming things in elliptic curve cryptography in a certified way. So this is certainly something that's possible. As I said, so elliptic curve, I think, elliptic curves are special in that they're, by their nature, that they're not too complex mathematically. You don't need a huge building like for, say, analysis, or if you want to do classification of finite groups, or if you want to do sphere packing. So it's a fairly bounded domain where you can, but with relatively elementary methods, you can still make a lot of mileage. But on the other hand, it's also extremely important to get the implementation right. So you can actually motivate to spend the time on doing things right, as opposed to, if you're implementing a web interface, then there might be less interest in actually certifying that everything is functionally correct. So I think it is a special field.
Okay. Do you want to add anything?
Well, I would just actually ask a question back to you, Ben, and maybe to people on the chat on, I think one of the reasons my group works on ECC is because it has this combination of implementations that need to be particularly fast. It has some interesting mathematical properties to prove about it, not just sort of it's memory safe or something. So it's got a combination of things, and that you can actually write fairly fast and verified implementations with some amount of work. You'll never have this like massive gap with real implementations people want to use. So that makes it a very good target for us. But I guess one question that keeps coming back to me is, well, what are the things that people who are designing elliptic curves today are worried about? So are you worried about like high-level proofs, about the math? Or let's see, high goes in different ways. Are you worried about the underlying math underneath the curve, that the equations are wrong or something? Or are you worried about the cryptographic properties that are coming out of it? Are you worried about the implementation? Are you worried about side channels? I mean, how would you rank the things that you would like to see verified about ECC?
Yeah, it's a good question. I think the one thing that people worry the most about is probably relevance at the moment with in a post-quantum environment. But we can't come up with a formal proof for relevance, so we'll have to settle for some other stuff. But yeah, I think it's different for everyone. I mean, some of us have more mathematical training, so I think in my case, having studied a lot of mathematics in the past, when I was sort of first coming to France and encountering a lot of this stuff, and they'd be like, yeah, well, we can now prove the elliptic curve group law, and I'd be thinking, yeah, well, we already proved that in the 19th century. It wasn't in doubt. What's the problem? But I know there are other people and students, for example, or people that are coming more from implementation directions, and they'll sort of go, well, hang on, here's this weird looking group law on some weird kind of curve, or even something like I haven't seen an Edwards curve before because it's not in the textbook. How do I know that this really is going to work on all of its inputs, or something like that? So there's on the one hand, there are people that will always be confident about that stuff, and on the other hand, there are people that won't be. There will be people that are going to think first and foremost about side channels, and other people who are going to think, well, it's something that'll be delegated, or like as if elliptic curve was kind of, cryptography was kind of modular, like, well, I'll come up with this algorithm and then someone else can do the constant time version. I'm not sure there's a very simple answer to this, and I think there's a lot of diversity in the ECC community. There's also, I think, the fact that a lot of the people that would be at this conference, and a lot of the people that would be interested in this, they're not necessarily developing brand new elliptic curve algorithms. They're using elliptic curve algorithms, and they're really interested in this from a user point of view. What can elliptic curve protocols do for them? And I'm sure they've got a whole bunch of other questions that wouldn't come to my mind. So I guess we've got as much of a diversity of preoccupations as we do on the formal method side, which is maybe not very helpful to you. So one thing though, so far we've mentioned, Bas was just saying that, if you can write a proof in mathematics, then you can do it in Coq or in F star. So Coq, for listeners that don't know it yet, because they haven't spent time in France, it's a sort of proof assistant named after the French national animal, which is a chicken. As a mathematician, it's something that I can kind of read it, but I'm pretty sure I can't write it. I'm not sure if it lines up perfectly with the way I do things, but I'm sure there would be a tool that does. So far we've talked about Jasmine, EasyCrypt, Coq, F star, Fiat Crypto, Hackle-Star. There are so many tools out there. How should we make sense of this? Why are there so many tools? Why are some better than others? If I want to start getting into formal verification, where should I begin, or what should I privilege here?
This is a super hard question. Bas, go for it. He seems to have an answer.
There are a number of places where one could start. There's a very nice book called Mathematical Components. This came out of the development of the classification of finite simple groups. That's a big project that was supported by Microsoft and INRIA, and was headed by Georges Contier, and a lot of people worked on this, and what grew out of this was a very well-developed library. And there's actually a book connected to this, which is aimed at mathematicians, and that's a very nice way of starting this. One thing that's unfortunately missing is the connection between that big library, which also contains obviously an awful lot of group theory, to the elliptic curve implementations. And that's something that as a community we're slowly working on improving. There's the Coq community is actually quite active, and it's becoming more and more structured. There's also the lean theorem prover, where a lot of mathematicians are currently gathering. The lean theorem prover is a new implementation basically of Coq, which has maybe a bit more automation, but it's not even entirely clear. It just seems to be somewhat more popular among mathematicians at the moment. If you're interested in more the computer science aspects, or want to prove things about constant time, then Coq, I think, is a very good place to start. So why are there so many different tools? Well, in part because we don't really know how to do things, and we're still experimenting a lot about how to actually develop such a tool. We're also still trying to figure out what mathematics actually is. I mean, there still seem to be mathematicians that think that mathematics is based on set theory, but there's no real proof assistant for set theory. So we're trying to explore what are the foundations for mathematics, especially if you want to include computation, and type theory certainly is a very good answer to that. But there are developments in the type theory world that are also very much connected to what's happening in the programming language world. F-star is also a very good system, but it's harder to write proofs in that system because there's no real language for writing proofs. You just write statements, and you hope that the automation of the system is clever enough to bridge the gaps between the systems. So I think for a mathematician, F-star would be harder to use, but that's something that so now I can have Kartik respond to that.
I don't know, maybe Bayo has his favorite tools as well, so maybe he should go first. Yeah.
Yeah, I think it depends on the level of automation you want to use in form verification. So calc is very nice, but to learn how to use calc, you need to take time. You need to learn how to formalize your proof, paper proof, and do that in a very formal way. And the other group is more like, so let's forget about all these formal languages, and let's try to let computers to find proof for us automatically as quick as possible. And that's why this F-star, even cryptolines, comes up. So basically, the goal is not to have a very rigorous or very formal proof written by hand. Instead, the goal is to try to let computers to find a witness or a proof for the correctness of the program automatically. Okay, so it's for me, I'm coming from verification model checking kind of background. So in model checking, that's exactly what we do. So basically, ideally, you just write a model for your program and you write a property of your program, and just how push a button technique will solve everything for you. Okay, and I guess that's where F-star as well, and also Cryptoline, the tools are trying to do similar things. But then again, I think for ECC, basically traditional model checking or automatic verification people, they're not so familiar with this kind of mathematics for ECC, and that's why we still need more specialized algorithms, for example, to help ECC community to prove the correctness of programs, or even such free, etc. So
to me, I would feel like, I agree with Bayo and also with Baz in a certain way, because it actually depends on where you're entering from. So at least with our students and people who start working on F-star and in our projects, we find that if you're coming in from a viewpoint that you know really well how to program, and you want to see your code run, because that's how you think. Even if you have to write an exponentiation function, it's kind of trivial mathematically. It's just a symbol, but to understand it, maybe you want to write that little piece of code and see how it exponentiates, whether it's in Python or whatever. If that's the way your brain works, then you want tools that let you in very quickly, and then you're maybe willing to stop and develop much more infrastructure to do deeper proofs. So my experience has been that automated tools like, say, Proverif for protocols or Cryptoline or F-star is semi-automated, kind of let you in very quickly. So very quickly you feel like, oh, I can prove things about factorial, about whatever Ackermann function, things like that I can do very quickly. I can prove my code terminates very simply and very, almost automatically. And you can get in very easy, or relatively easy, let's say. But then when you're trying to do like a large theorem about ECC or about some other topic like that, I feel like most of these tools end up being at the same level of automation. You have to think through the proof in the same way, structure it. Even in F-star, we end up using a lot of tactics and doing the proof more or less like you would do it in Coq. It just uses a different, let's say, proof checker, but really it looks very much like how you would do it in Coq. So yes, if you're doing a proof of a math theorem, most likely you're going to have to learn one of these systems really well, and then you can execute it fairly after. Once the learning phase is over, and Baz was saying that it's getting better and better for Coq, F-star, the learning phase is still a bit steep, I would say, at least for deep proofs. For shallow proofs, it's very quick, but for deep proofs, it takes a bit longer. So I think that's the kind of mentality difference I think that these different tools are sort of targeting. None of us are, I think, I would say, ready for like mainstream developers to start using them immediately. But the more automated tools, at least they can do something immediately, and then maybe they can do deeper stuff later. I think that's how I would summarize the status, I think.
If we come back to this point of accessibility and getting into it, and what Baria was saying about basically about paper proofs, if while I'm maybe one day I'll learn F-star, for example, but in the meantime I'll definitely be writing papers. If I'm a mathematician, I'm going to be proving theorems. If I'm programming, in my crypto papers, there's going to be theorems, there's going to be pseudocode as well. I'm going to have my own implementations, but then, when I'm publishing the thing, I'll be writing out some sort of pseudocode, and then what you hope is that other people are going to use your theorems and they're going to use your code one day, or use the idea. How should I be writing these things? How should I be proving my theorems on paper, and how should I be writing my pseudocode? Because both of these are a kind of formal specification of something at a certain level of quality, maybe not high enough. How should I be doing that to make the job of writers more easy, to make it easier to translate these things across into formal verification tools? What are some if you wanted all of the ECC participants listening to make your jobs easier, what should they do in their proofs and what should they do in their pseudocode?
Well, first thing I would say, at least, everybody has their own asks, I'm guessing, but it's a syntactic, actually. I saw this nice talk by Doug Stebler a couple of years ago. I don't know if he's on the chat. I don't think so. Where he described a LaTeX, format for writing oracles in your paper. He said, let's just standardize the syntax for writing oracles. Let this be a typed syntax. So you actually always say for every variable what its type is, and you declare it. So there's a uniform syntax for writing stuff, right? That I think already helps, because it allows us to not have to go through papers in a field which we don't understand in order to extract out, say, what the underlying chem description in PQ candidate number 3 is, right? So that level, at least, I think that would be the first step, right? Then if, for example, you're doing a proof, maybe the individual steps of the proof, you still want to have the freedom to write it by hand. But say, again, I'm going back to game hopping because it's easier. If you have a sequence of games and you actually list and perfectly in a nice syntax write down the sequence of important games, as many papers do already. Now that already helps, because now we have like concrete targets that you have a game A and game B, and you have to prove that A is equivalent to B using some set of rules. And so you can actually see in your head how the machine will do the proof, right? If you can't see in your head how the machine can figure out how to go from point A to point B, then people who use formal verification tools are extensions of their machines often. So we don't have too much extra thing we can bring to it. We just can help the machine, So we have to be able to see that path. But I can't say it anything more concretely than that, I think.
Okay.
There's a nice initiative called HexSpec or RedSpec, which I think Kartik is also at least partially involved in. And there the aim is to write a very, especially this especially deals with pseudocode. And so people would write pseudocode in their paper, but there's now so this hexspec is a project to actually isolate a subset of Rust in which you can basically directly write your pseudocode, but it's a functional subset of Rust. So in that way, you can quite easily translate it, in this case to F-star, but translation to Coq should also be possible. So there you would already have a common language. So if you now propose a new cryptographic standard, you could write your pseudocode in that language, and then the automated tools could already start doing their work, and you also have directly a translation to the proof assistants from where the experts in proof assistants can pick it up. So I think that this is one very clear initiative that I think deserves some support. Yeah, I completely agree with the remark about game hopping, which really helps just to write down the games in between. I think other parts of cryptography where it's not just game hopping. For example, I'm thinking about some of the work in consensus protocols that we've been looking at, secure distributed systems, where also, of course, this is not directly elliptic curves, but it's certainly a part of cryptography. There it's still much more unclear how to actually write the security proofs. So this is certainly something that I think work is needed, and this is both writing precise proofs on paper, but also in the machine. And I think because of the state we're now at with the proof assistants, we can really help and bring the expertise from programming languages and from logic to help to develop a common framework for how to write these kind of proofs.
Yeah, I think even human-readable security proofs would be a good start. Well, yeah, I've got a question for you. Since we've been talking about handwritten stuff, and Tanya Langer was asking, crypto code is not really written in high-level languages, and there's already a big volume of handwritten formula, which is going to be hard to replace for performance reasons. Code that already exists, and then in the future, I think there's always going to be people saying, no, but my assembler will go faster than what's been generated. Can we hope to verify this or to fix this situation?
Let's say so we are doing semi-code verification in our group, and so I think it's probably fair to say for this very low-level arithmetic code, even in assembly, I think at least for ECC, we've done pretty much all the code we can find. So unit P curves 224, 256, and 521. All arithmetics has been verified, and also the Bitcoin field arithmetic. And also we are working on this BLS 12-138. So these are written in assembly code, so we can work on that. So, but unfortunately, our experience is that most of the code we need to contact programmers for the spec. Okay, even for this very basic arithmetic in the field, in extension field. And the reason is that for ECC, for optimization purposes, sometimes the range can be slightly more than the prime field range. Okay, just to save some carrying time. And as a verification team, we have no idea, what kind of real range programmers is worried about. So in OpenSSL, I think there are some comments to help us to say, well, this is a range. Programmer is assuming about the input and also the output ranges. And so, okay, I suppose if, all the assembly programmers, or even for the C programmers, for this very low-level arithmetic, so the spec is quite easy, right? Just do a multiplication or cooperation. That's very easy. But then we need a range. That's the thing, we just cannot guess in order to prove. So if we can just write comments, then I think our experience that for this BLS 12 thing, I think for 2 months, we can verify, actually during this summer, we just verify the whole tower. So, that's 12 elements, and each element is from a prime field of 381 bits. The multiplication can be done, from a very basic prime field with 381 bits up to these 12 elements of this field elements. So can be done in 2 months. But then we need to contact programmers. So that's the current status.
Okay, yeah, it's really interesting. If we stay on the implementation side for a moment, Pierre Gaudry has a question of nowadays a lot of the code that we write, in the end, it's going to be run in a web browser. Okay, that's our new sort of universal platform for some applications anyway. Are there any problems or solutions that are specific to this particular use case of the code that's running in a browser? Do we have formal methods for this situation, side channels, all this sort of stuff for this situation? Where are we with respect to code that will run in a browser?
So there's 2 things in the browser, right? There's inside the browser and things that you download from the internet and run on top of the browser. So things like Hacklestar is used in Firefox and Fiat Crypto is used in Chrome. So underneath the hood in browsers, they're already using formally verified crypto, and I'm hoping that soon all of the crypto these browsers will use will be formally verified. All browsers, right? But if the question is about code that is downloaded and run, as an application on the browser, now that's a very interesting zone. I agree. So we have a compiler from F-star to WebAssembly, and so you can download, say, Hacklestar or even an implementation of Signal written in WebAssembly and run it. We think WebAssembly is the right place to target a lot of effort and tooling right now, because it's way, compared to JavaScript, there's no comparison in terms of the levels of guarantees you can achieve. But there is still a lot of open questions, because WebAssembly obviously needs its own runtime, needs its own sandboxing, and we don't fully understand what the side channel ramifications of writing and running code in WebAssembly in your browser are. There is some preliminary work called CT-WASM coming out of San Diego, I think, for constant time WebAssembly. But that's just constant time, right? And we have to go way beyond that. So I think more generally, even getting outside the web, the whole notion of side channels is indeed a place where we could do much better. I think a lot of tools have essentially solved the problem of whatever constant time code in the sense of protecting code, secret independence, don't branch on secrets, and don't use secrets as indexes. And that kind of thing is very easy to check in almost all the tools that we have. But beyond that, if you want to go to DPA, false, Spectre, this kind of stuff, which is again, and basically cache flush reload kind of attacks that are browser specific, there we start to get much weaker guarantees right now, because we don't really have very good models for these. So I would say that's where we are. But indeed, it's an important question.
And what about code that's supposed to run in smartphones? This is a question that Dan was asking. I mean, we're used to looking at, well, we're generating really fast assembly code, or we're compiling to C that's going to run on a PC, and that's I think what most of us are working with. But I mean, a lot of the code is going to have to run in, or already done in smart codes. None of that smartphones, and none of that is verified. What does the future look like there?
Well, I mean, the OpenSSL code that Bayao has verified and Hackle code also runs on smartphones. So I think, okay, there's 2 ways of looking at it. One is, what about relatively low-end ARM devices? What kind of guarantees can we give there? And of course, verified C implementations like Hacklestar, Fiat Crypto, they are not on smartphones. They are being used on smartphones right now with their 32-bit versions or whatever. And in fact, maybe you could optimize further for more and more low-end devices, maybe going all the way down to embedded and IoT devices. Conversely, if you're thinking specifically about smartphones, well, the latest Apple iPhone is no less powerful than my laptop, at least. So maybe this is just a temporary phase, and within 3 years, all smartphones will have such powerful processors that you won't have to do anything special, just run the same code that you would run on your desktop over there, and it would work. If the question is about side channels, then I don't know well enough, actually, so I don't know what you can do there.
Okay, yeah. We're coming to the end of this session. We're not done quite yet, but I just want to remind everyone before they click off that in a few minutes we'll be moving over to the virtual coffee room where you can bring your own coffee on wonder.me. The link is in the Zulip, I think in the general stream, and I think we can continue a lot of these conversations there. It'd be really nice to see you all. Just to head towards an ending with this, there's a question from Mathilde Chenu, and this is getting back to the Cathedral of Mathematics and the sort of the new Gothic architecture phase of elliptic curve cryptography. The question is, are new tools needed or being developed for verification of isogeny-based cryptography, or existing ECC tools sufficient?
I'm not aware of any specific tools that are developed, but isogenies are a respectable part of mathematics, and there's no problem in actually verifying this mathematics. And I mean, as mathematics goes, it's not particularly complicated, and one could hope that one could use one of these embedded low-level languages like Star or similar like Fiat Crypto or related tools to actually program the corresponding algorithms and prove them correct. So I think most of the infrastructure is there. It would be mostly a part of developing the libraries, and I would guess that quite a lot is already there in just general infrastructure.
Yeah, I mean, I would agree. I mean, let's say that in terms of tools, there's nothing new to be done. But in terms of libraries, probably there is certainly work to be done there. We are still playing catch-up, so we're all doing ECC more or less. But some people have already started verifying lattice-based crypto because it's kind of easier. And so moving slowly forward, I don't think any project has yet tackled isogenies, but I don't see any strong reason why that should be harder. Having said that, everything is hard, so it's not like it's going to be automatic.
Yeah, but then none of us got involved in this to do the easy stuff. So yeah, there you go, everyone. There's no excuse for not getting to work on this. Just to wrap up, if you could each in just very quickly say what's the next frontier of verification? Like what's next for each of you, or what do you think would be a good common goal?
I think one of the things is interoperability. We need to have a better interaction between the various tools, because there's too much work being duplicated at the moment, and I think we now also have a better sense of what we actually need, and I think there's good work on the way of actually connecting the tools and connecting the libraries. Apart from that, we also need to connect the high-level mathematics, the big mathematical libraries, to the low-level implementations, and that's also starting to be feasible, but there's certainly work needed there. I think those are at least two main points.
Okay.
Yeah, and for me, I would say that integrating these verification tools in a way that developers and cryptographers can get some things very quickly is still, like, I would say, very, very important. I mean, for people who use Rust, for example, at least memory safety is now done, right? So what if we could provide simple tools to say, okay, now constant time checking is done. It's nothing to be worried about at all. It's just like as you program, it's done automatically, and more things like that. What can we give you for free so that you can then focus all the efforts on doing more interesting parts of the proofs? Would be, and how to integrate this with the normal development workflow, design workflow for things like ECC would be, I think, the next frontier.
For me, I think increase that kind of level of automation will be the first priority. So basically, I don't think any tool can just like really push button. So compared to hardware verification tools, there are tools which you actually literally you just push a button, and the tool will say, well, the circuit is verified. But we're not there yet, unfortunately. So that's would be the utmost goal for my part.
Okay, well, I'm going to declare that Baoyao Wang, you are the last word in formal verification for ECC, because we have to end the panel here. Again, thanks to the three of you for participating. It's been really interesting for me, and I hope for you and for everyone else as well. I'd encourage everyone to join in the coffee break basically now. But yeah, thanks once again, and enjoy the rest of the virtual workshop.
You are currently the only person in this conference.